Let us start this lecture with a thought process from Vinoba Bhave, who was an ardent supporter and follower of Mahatma Gandhi, who says, if a man achieves victory over this body, that means one's own body, who in the world can exercise power over him? He who rules himself rules over the whole world. This is one of the important aspect of human life, that to win over or his own, not only the body, but also the mind, and that is the sole objective of education, and we must look at it seriously. Let us now recall what we learned in earlier lecture. In the last lecture, we basically started discussion on the effect of propellant temperature on burning rate, and we looked at how it is important, and the propellant burning rate gets increased with propellant temperature, and this effect is more predominant at the high chamber pressure. And later on also we moved into various kinds of burning reagents, namely the normal burning, the plateau burning, and also the mesa burning, and we have seen that this plateau or the mesa burning are a part of basically double base propellant. Sometimes in case of composite propellant burning, you can also observe plateau burning. And today we will look at again this Saint Robert law, but in the last lecture we also discussed about another two law which are not being used very much, but one of them is more generalized, that is R dot is equal to A P C power to the n plus B, and for artillery generally R dot is equal to A P C plus B, and that is mean for high pressure. There will be very high rise of pressure in the artillery, and that will be affecting the burning rate also very much. So, today we will be dwelling upon little bit on the practical data on the burning rate, which can fit into this Saint Robert law. So, let us look at certain characteristics of few operational solid propellant. You can look at this table. This is dB is basically double base propellant. Metal content is almost, it is 0, and its flame temperature is 2550 Kelvin, burning rate is 1.2 to 30 mm per second, and the pressure index is 0.3, and ISP 220 to 230, and the process of making the grains, propellant grain, is basically extrusion. And of course, the next one is a combination of the double base and then ammonium perchlorate with metal additions, and the metal content is between 20 to 21. There is a significant change in the temperature, 3880 from around 2550. Burning rate is in a similar range, and the pressure index has increased from 0.2 to 0.4, and beside this there will be significant increase in specific impulse from 220 to 260 to 265, and again it is the extrusion process is used for fabrication. And then another, let us look at double base propellant with AP and with the explosive, that is high melting explosive along with aluminum powder. Aluminum powder is around 20%, temperature has increased maybe around something 120 Kelvin, and the burning rate is similar range. There is a slight increase in pressure index and also slight increase in specific impulse. The solvent and casting method is being used for processing of propellant grain. And you can see also polyurethane AP and aluminum, the temperature has little bit reduced, also the higher range of burning rate has reduced from 30 to 23, but what is very important is that this pressure index is very small, that is 0.15, and there is not much change in specific impulse as compared to other propellant, particularly these two, and the process is casting method. And if you look at most used composite fuel in propellant is your CTPB, cycloterminated polybutadiene, and hydroxyl terminated polybutadiene, these two, STPB, AP and aluminum. So, if you look at temperature, both of them are almost same, and the burning rate little bit lower in case of CTPB as compared to the STPB, and the pressure index is same, and then the ISP is almost it is same, and the process is both are casting. You can look at also PVAN, another, if you add of course the polybutadiene acrylic acid, that is PVAA along with AP and everything, the burning rate is little lower as compared to others, and the pressure index is 0.35. And ammonium nitrate and polymer, if you look at without any metal content, the temperature is quite low, that is 1550 Kelvin, and the burning rate is also lower range in this case, and the pressure index is very high among all these things. So, also the ISP is quite low, that is 190. And keep in mind that if you could observe the temperature and specific impulse, density, burn rate, pressure exponential vary to some extent with specific composition, except few exceptional propellants where which are not being mentioned, maybe except this ammonium nitrate and polymer and also polyurethane. The others pressure index almost similar, and then also the temperature is also almost similar. And keep in mind that this pressure index N for practical propellant lies between something 0.15 to 6, sometimes people say it is basically 0.2 to 0.6. And we will see little later on that for stable operation it must lie between 0 to 1, and if it is 0, the N is 0 is basically corresponding to the plateau burning that we have seen, and that means the burning rate will not be changing with respect to the chamber pressure, and that is of course good, but it can lead to instabilities, and also instability means pressure fluctuation will be there, because the dark zone and particularly in a double base propellant will be higher, and then also it may lead to the extinction of flame. And 1 is a very high value, and then it may lead to very higher rate of change of burning rate with the pressure change, and this is really may lead to the explosion also, particularly when one operates at a high pressure of the combustion chamber. So, therefore, one has to be very careful about that, and while designing, and we will discuss more about this range of pressure index little later on, and argue that which is about the stability or the stable operation of the solid propellant rocket engines. So, let us now look at an example, and using this Saint and Robert law, and see that how we can use it. Let us say that during testing of new propellant in a strand burner, the regression rate at 2 chamber pressure is 7 and 17 megapascals are found to be 25 mm and 45 mm respectively. If the regression rate happens to be followed the Saint Robert law, determine the chamber pressure when it regresses at 35 mm per second. So, let us look at we need to basically find out the chamber pressure PC to find basically PC at when R is equal to 35 mm per second. And what is given is that if I say the chamber pressure 1 P1 is 7 megapascal, then R dot 1 will be something 25 mm per second, whereas PC2 is something 17 megapascal and R dot 2 is 45 mm per second. We need to find out basically chamber pressure. So, solution we can, and for this purpose we can use the Saint-Robert law, that is law. We will get R dot is equal to A P C n. Keep in mind that A is A divided by T I minus T P P C n. And if I want to find out P C from this expression, that I can get R dot A power to 1 by n. In this case, neither n, that is the pressure index, n is your pressure index, index is known, nor A, this is not really constant, A is a constant. And keep in mind that the temperature T p is remaining constant, and this is the same propellant. Therefore, T I, that is the self ignition, is remaining constant. Therefore, if you look at A is constant, small a is constant for all, for this case, for at the both the pressure. So, therefore, we can use that by using, if I say this is equation 1, this is your equation 2, equation 1, we can get R 2 by R 1 is nothing but your like P c by P c 2 by P c 1 power to the n. So, I can get basically this R 2 is 45 and this is 25 and P c 2 is your 17 and this is your 7 and this is power to the n. So, therefore, n I can find out very easily. If I substitute these values, I can get 0.662. This is your n values. So, therefore, I know this n, I need to find out A. So, A I can get we can get A is equal to R dot by P c power to the n. So, if I take for chamber pressure 1, that is your R dot is 0.025 and one has to be careful about the units. So, I will be using SI unit for this expression, and P c is your 7 megapascal, 7 into 10 power to 6, and n already we got it, that is 0.662. So, I will get something 7.35 10 power t minus 7, and we can determine P c by using equation 2 as R dot A 1 by A, and R dot what is given is something 35 mm. So, this will be 35 mm means I will be using the SI unit, therefore, this will be consistent. So, 7.35 10 power 7 1 by 0.662. So, I will get something 11.57 megapascal, and you can check that this is basically range between these two as 25 mm at 7 megapascal and 45 mm per second at 17 megapascal. Therefore, it is coming in between. Keep in mind that this is not linear, and this is a expression is a non-linear in nature. So, therefore, we will have to care. A question might be coming to mind, what I will do? It is very important to use this whenever you are conducting experiments, and then also looking at several data, you can find out this. Later on, we will take an example how we can use the burning rate expression to find out dimension of the propellant grain like length and diameter, and then we can also estimate the thrust and other things from that. So, we will take little more complex example little later on. So, let us now look at what are the methods of enhancing the burning rate or rate of a solid propellant. Let us look at what are the methods of enhancing burning rate of a solid propellant. It is not only the enhancing of burning rate, sometimes we may need to also reduce the burning rate or changing the characteristics of burning rate, particularly whenever we are getting something mesa burning or the plateau burning, we may change by adding some kind of chemical, changing this reaction rate in various zones that we have seen depending on the type of propellant is being used. So, therefore, let us look at what are the ways of doing that. Basically, all the methods can be broadly divided into two categories. One is by changing the propellant formulation and also the method of manufacturing. As I told that earlier, if it is extrusion process and if the or the casting, there will be difference in the changing the properties, and so also the propellant formulation. If the composition of the propellant is changing, then naturally the burning rate will be changing, so also the pressure index. Beside this, by changing the operating condition of the rocket motors, for example, the chamber pressure, if it will change, burning rate will be changing, we have already seen. So, also if it is the temperature of the flame is changing, the burning rate will change, and if the temperature of the propellant, that means is changing. So, therefore, the burning rate will be also changing, that we have seen. And let us now look at one by one, and if I consider the changing of the propellant formulation, it can be meant for both for composite and double base. Let us look at how can you do that. By adding a burning rate or a catalyst generally, which can be 0.1 to 3% by weight, we can modify the burning rate. We can increase it, we can decrease it, right, depending on what is required. For example, in case of composite propellant, generally copper chromides, ferric oxides and several like metal powders are being used to enhance the burning rate. And similarly, in case of double base propellant also, copper or lead, salicylate, even graphite or lithium fluorides are being used for enhancing the burning rate. However, sometimes this double base propellant can behave in a little different way. it may go for super burning stage, like where the N will be a very high values, and it may lead to the plateau burning, it may be also having the mesa burning. Now, to suppress those things, and also people use it. So, therefore, one has to be careful in using the catalyst for enhancing the burning rate. And in case of composite propellant, as it is heterogeneous in nature, the particle size of the oxidizer will be also dictating the burning rate. If the particle size is reduced, then the burning rate also will be getting increased, because of fact that there will be coming closer to each other, and then there will be diffusion will be taking place with a shorter distance, and then the burning rate also will be increasing. And we will be discussing little bit more about it little later on. And beside this, in case of composite propellant, one can enhance the burning rate by increasing the oxidizer and fuel percentage. Like means, when you increase the oxidizer percentage in a propellant, then there will be basically the oxidizer and fuel ratio will be increasing for the same propellant, because of fact that the oxygen level in a oxidizer in case of composite propellant, whether it is a ammonium perchlorate or ammonium nitrate, will be increasing. So, therefore, one can expect it to have a higher temperature and then also the higher burning rate. Beside this, if we can use certain binder or plasticizer with higher heat of combustion, so therefore, there will be also increase in the flame temperature, and because of higher heat release, and then there will be increase in burning rate. So, also there is another way of increasing the burning rate, that is by changing this manufacturing of the propellant. If I will take these wires, particularly metal staples or metal wires, and embed in the propellant itself, if I consider let us say end burning grain kind of things. This is your nozzle and this is your propellant, right, and propellant kind of things, and this is your end burning propellant. And if I add some wear here, let us say these are metal wires are being embedded. Then what will happen, because this will be receding, this surface will be receding as it getting burnt, right, it will be receding toward that, and as a result this heat, whichever there might be a flame here over, heat will be transferred to this metal, and then this propellant around this will be getting degraded or getting burnt due to the heat transfer. There will be heat transfer, and then propellant will be degraded, and as a result there will be increase in burning rate. And keep in mind that this is generally used for end burning grain, and generally the silver metal is being used, but if you one can also use other metal. If you look at the silver's conductivity will be higher, therefore, it will be having higher burning rate as compared to the aluminum, and it's of course its burning rate due to this metal wear or the metal staples. That means, this will be kind of staple which will be there. This is your metal staples which will be embedded in the propellant. As I told earlier, the burning rate will be depending on the size of the wear, that means diameter, and also the number of wears per unit cross sectional area. And also the people use the metal staples, so that you can also get a higher rate of burning rate. By changing the operating condition of the rocket motor, the burning rate can be changed, and it will be depending on the following conditions. One is of course the chamber pressure, as the gas phase reaction plays a very important role in providing the heat to the propellant burning surface, because when the pressure increases, the flame will be coming closer to the regression surface. And also the if the initial temperature of the propellant will get increased due to this ambient higher temperature, then there will be also increase in burning rate, and the combustion gas temperature will also enhance the burning rate. But keep in mind that the combustion gas temperature will be basically depend on the composition of the propellant and also the heat loss from the combustors. If the heat loss can be minimized, then the actual combustion gas temperature will be higher. Beside this, the flow of hot gases on the port area also will be affecting the burning rate, and if it is beyond certain threshold value, then there will be increase in the burning rate, what we call it erosive burning, and we will be discussing more about it. And apart from that, the rocket engines may really be accelerated, and also it may be spin around, and if the spinning is occurring, so there will be acceleration of the vehicle and so also the fluid, and it may lead to also increase in the burning rate. We will be discussing some of them in the next class, and with this we will stop over, and thank you very much.